Okay, I think we're live. Good morning, everyone. It gives me great pleasure to introduce to our first talk during the main COMSNETS session. It will be a keynote talk by Professor Lili Chu from University of Texas at Austin. Her talk title is going to be Acoustic Tracking and Its Applications. Professor Chu has been a professor at Austin since 2005. Before that, she actually spent a number of years in Microsoft Research in Systems and Networking Group. She's the current chair for ACM SIG Mobile, and she's done a lot of fascinating research over the years. I mean, she's an IEEE fellow, she's an ACM fellow, she has an NSF career grant, a Google faculty research, Best Paper Awards and MobiSwiss and ICMP. She's also supervised a PhD dissertation that's won the SIG Mobile Best Dissertation Award. The list goes on and on, right? So without any further ado, I will hand over to Professor Chu to give us a fascinating talk. Over to you, Professor Chu, and thank you for giving this talk.
Thank you so much, Rajesh, for your kind introduction, and thank you to COMSNETS Organization Committee for the kind invitation. It's my great pleasure to present some of our recent research on motion tracking and applications. Can you all see my screen? Great. Motion tracking has lots of interesting applications. It not only allows us to play interesting motion-based gaming, but also interact with VR, AR devices, as well as enabling smart driving and also contactless health sensing, contactless control, which is very important, especially during pandemic. A natural way of enabling motion tracking is using camera, but the moment you turn on the camera, it raises significant privacy concern. Moreover, vision-based solution also face challenges from the range, field of view, and also expensive energy consumption. Radio frequency can also be used for motion tracking. For example, Wi-Fi has been shown to enable motion tracking, but due to relatively large wavelengths, it takes a significant bandwidth in order to achieve high accuracy. 6G gives accuracy improvement, but it's still not widely deployed yet. We know that speaker and microphone are everywhere. So can we use acoustic devices for motion tracking? So for example, what we could do is use commodity speakers such as those you bought from Amazon for $10 to transmit inaudible sound so that it does not perturb users. And then use the microphone on your mobile devices to receive the sound and enable real-time motion tracking. Not only acoustic devices are widely available, but also due to its low propagation speed, it has potential to achieve high accuracy. Moreover, acoustic signal has a low sampling rate, so it enables efficient software processing and high energy efficiency. So in this talk, I will briefly introduce some of our motion tracking work. First, we'll look at tracking a mobile device. We let a speaker emit audio signals in inaudible frequencies, such as frequency above 17 kilohertz. And then the microphone on the mobile device will receive this inaudible sound and use the received sound to track the device in real time. Our first work uses Doppler shift for motion tracking. As we learned from our high school physics, due to movement, there's a change of frequency in the received signal. And the change of the frequency is directly proportional to the velocity. Therefore, by measuring the frequency shift, we are able to estimate the velocity. So what we could do is perform short-term Fourier transform on the received signal and find the peak frequency and map the peak frequency to the velocity. So first, let's take a look of the case where speaker's distance are known and the initial position are also known. And then we see how can we locate a device based on Doppler shift. Suppose we know the initial distance to each speaker. Then based on the estimated velocity, based on the Doppler shift, we can estimate the new distance to each speaker. How well can the distance estimation be? So here we plot the distance estimated using Doppler shift versus ground truth. As you can see, these two curves match very well, even after a few seconds. So this indicates the feasibility of using Doppler shift for distance estimation. Once you get a distance from each individual speakers, if you have distance from multiple speakers, then we can run triangulation to find the position of the mobile device. Next, let's take a look at how can we estimate the distance between the speaker. One way is we can just use a ruler to do the measurement. But to make it more convenient, we just let the user swipe a mobile device across both speakers. As we know that as the user is moving towards speaker 1, the Doppler shift is positive. As the mobile device moves past speaker 1 and start moving away, the Doppler shift becomes negative. Then we can just watch the change of the sign of the Doppler shift to detect the location of the speaker 1. Similarly, we can detect the location of speaker 2. Then we can use the estimated velocity based on the Doppler shift to calculate the distance between these two speakers. But the initial position of the mobile device, in many cases, the position is unknown. There are multiple ways of estimating the initial position. In this work, we use particle filter. Basically, we initially allocate many particles in a given space. Then in each movement update, we remove particles that give infeasible movement. And then we update the position based on the average movement of the remaining particles. And we found this particle filtering quickly converged to the right position. And our first version of motion tracking enables centimeter level accuracy. This is already orders of magnitude better than existing accelerometer-based approach because the accelerometer measures acceleration, which has a faster error accumulation due to double time integration. Can we do better? Because in many cases, we might want to have millimeter level accuracy. To further improve the accuracy and avoid error accumulation, ideally we want to directly estimate the absolute distance. FMCW is a well-known technique to estimate the absolute distance between two devices, but it assumes the synchronization between the transmitter and receiver. To overcome the synchronization issues between the transmitter and receiver, because our microphone and speaker run separate clock, what we do is we first estimate the reference distance and then estimate the change from the reference distance to get the new up-to-date absolute distance. And we combine that with the velocity estimated based on Doppler shift. Furthermore, we can also leverage IMU when available. IMU not only allows us to estimate the acceleration, which can be used as another variable in the optimization, but also it allows us to facilitate calibration between the clock drift between the two devices. And this plot shows the performance of our two different motion tracking. The top ones are based on the Doppler only, and the bottom one cat based on Doppler and the FMCW with our synchronization approach. As we can see, the second generation achieve better accuracy. We put together a demo to showcase how well it works in practice. As you can see, we use internal speaker of the laptop to emit inaudible sound, and the smartphone running our app real-time analyze the received audio sample to estimate the position in real time and send back to the laptop to update the position and the game state. And this demo uses 4 external speakers to emit inaudible sound. And again, the smartphone running our app real-time analyze the acoustics received sample to real-time update the position in 3D. And we can use it to interact with regular games or apply it to VR, AR games. We can further apply it to enable motion-based TV control. And also our motion tracking is light enough. The app can also run on the smartwatch. And here we show that the user have 2 watch in the hand and each one can individually track their motion and they don't have any interference. And even it works even under slight occlusion. So far, I have shown that we can use acoustic tracking to enable tracking on a smart device. But sometimes you may want to directly use your hand to control TV, VR, AR. In this case, it's, your hand may not have a device. So how can we enable tracking in such scenarios? So this is what we call the device-free tracking. In device-free tracking, as you can see, both the transmitter and receiver are static, but the target that doesn't have the device is the one that may be moving. So in this case, we have to rely on the reflected signal. This reminds us of RF radar, but existing RF radar are bulky and expensive. It takes a huge amount of bandwidth and also requires special hardware. Our goal is to enable device-free tracking for mobile devices so that we can just directly use our finger to interact with smartwatch, smartphone, and VR, AR devices. The good news is that phase change is proportional to the distance and wavelength because the acoustic signal has a small wavelength in inaudible band. So phase-based tracking enables us to achieve fine-grained positioning. In particular, 1 millimeter finger movement results in 0.21 pi phase change, which is easy to notice. But the main difficulty of using reflected signal for motion tracking is that, first of all, it has a low SNR because the reflected signal decay much faster, even in free space. Moreover, we receive reflection from multiple objects, not only the objects from the target, but also the surrounding furniture, walls, and so on. So how can we cope with multipass? Our idea is that we will estimate channel impulse response. At high level, channel impulse response captures channel profile at different distance. By estimating the channel at each distance separately, we can estimate the position. So here is an example show that we have 3 objects at different distance away from the target. By tracking the phase change of the channel tab corresponding to each of these objects, we can simultaneously track these objects. And this figure shows the performance result. The green curve shows the reference trajectory, and the red curve shows the trajectory, the finger trajectory, user try to trace through this reference trajectory. As you can see, these two match pretty closely, which indicates that our tracking is accurate and easy to use. Next, I show a quick demo of how it works in practice. So in this case, we let the smartphone speaker emit inaudible sound, and the microphone on the smartphone receive the reflected sound from the hand and able to use the reflected sound to track the hand's movement in real time and update the game state. Our update rate is 5 milliseconds, which is more than enough to enable real-time gaming. So far, I have shown that it is feasible to use acoustic signal to enable device-free tracking, but this works over relatively small distance. Is it possible to further enable room-scale device-free tracking? And the use case is for smart speaker. A quarter of US households own a smart speaker, and 40% of them own multiple smart speakers. Current smart speakers use voice-based interaction, but it faces challenges under quiet environments, noisy environments, and also complicated operations, such as if you want to choose multiple menu items and different options. So gesture-based interaction seems complementary, and it works well in all these challenging environments voice-based tracking face. We use acoustic device-free tracking because the smart speaker comes with speaker and microphone array. And also acoustic tracking has been demonstrated to achieve high accuracy, low cost, and privacy preserving. But existing device-free motion tracking has a limited working range and does not leverage the smart speaker setup. So in this work, we first improve several approaches in the signal processing domain. We convert the raw audio signals into distance and AOA 2D profile by using an enhanced version of 2D music. So in the ideal case, what the profile will show is the target locations. But in practice, there are multiple challenges. For example, when there's a low SNR, then the highest peak may not correspond to the ground truth because of the extensive noise. On the multipass, you may see multiple peaks. Again, the highest peak may not necessarily at the position of the ground truth. Furthermore, with fast movement, the Doppler shift will make the ground truth deviate from the highest peak. So all these make traditional signal processing insufficient to work. Therefore, we combine signal processing with machine learning to further enhance the accuracy. So we first apply signal processing approach to separate the target location from the background. Then we use the profile generated from the signal processing and feed that to the recurrent neural network to explore the temporal relationship of the target movement, and then output the target position. More specifically, we run 2D music profile and generate the profile for each time slot. And then we feed multiple profiles along with the current profile to the recurrent neural network to output the distance and the angle of arrival. Looking into each of the one recurrent neural network stage, our network architecture is very simple. We use a pooling layer to reduce the input size and a hidden layer to extract feature, and then another hidden layer to combine the extracted feature from the current 2D profile with the previous context, and then output the distance and AOA. And we are very interested to see what the context information is. And we perform correlation between the 5 context neuron with 5 physical meaningful information. The one is distance, and then AOA, radial velocity, tangential velocity, radial acceleration, and tangential acceleration. Interestingly, we found the first 3 neurons has a very high correlation with the distance, AOA, and radial velocity. So this suggests that the RNN is learning something useful. And then we basically take the training data collected from our lab and then applied it to the testing data collected in different locations. And we found that the performance is very similar. They all achieve around 1 to 2 centimeter position error. So this is very robust to the environment. Let me show you a quick video of how it works. Here we have a speaker and 4 microphones set up with a barrel board and connected with a laptop. And the user 3 meters away is moving the hand, and the speaker emitting audible sound, and the microphone would receive the sound, and the laptop process the received sound to real-time output the position. We instruct the user to trace a few standard geometry. Of course, the user's actual trajectory can deviate from that. But as you can see that the tracked trajectory is very close to our intended trajectory. Part of the error comes from the user's movement. Part of it is from the tracking. And as you can see that more or less it follows the user trajectory, and it enables centimeter level tracking in a room scale network. So far, I've shown you that it is possible to use signal processing alone to do motion tracking, and also using signal processing plus machine learning to enable motion tracking. Another interesting question is it possible to use a pure machine learning technique to enable motion tracking? Why is that interesting? Well, scientifically, it will be interesting to see if a pure data-driven approach can outperform a signal processing algorithm designed by experts. Practically, this may give a potential to achieve a higher accuracy and also inform design of future signal processing algorithms. So let's take an example of range-based approach. One of the most widely used range-based approach is FMCW. It's basically transmit a cosine wave whose frequency linearly changes with time. At a high level, through signal processing, the FMCW profile will have a single peak, and the peak is at the position of the target. But due to noise, we may see multiple peaks, and the ground truth peak may not necessarily be the highest. Due to multipass, if you have multiple objects and these objects are well separated, then we will have multiple peaks, and the target peak may not necessarily be at the highest peak. And when these two objects are close enough, then they will interfere and have a merge peak. In this case, the highest peak can be arbitrary depending on the relative position of these objects and their relative refracted signal. So due to all these challenges, just by simply picking the peak from the FMCW is not robust. So we could try to design neural network and feed different type of data to the neural network. There are multiple options. In FMCW processing, the receiver will first receive the raw audio sample and then mix the received signal with the transmitted signal, and then apply FFT to generate a FMCW profile. So we can feed data from each of these FMCW processing stage. So one could either feed a raw audio sample to a DNN, or feed a mixed signal to a DNN, or feed a final post-processed FMCW profile to a DNN. Which stage yields the best performance? Through our experiments, we found that feeding the raw data gives the lowest error. This is likely because through some signal processing, we may accidentally remove some important features which are hard to recover in the machine learning stage. But in order to enable a raw data-driven approach, we need to generate high-quality data. How to get this high-quality data? One way is we can conduct a large-scale measurement using different phones at different locations. This is time-consuming. So our approach is using realistic simulation. We try to enhance the simulator to make it more diversified, but capture the realistic artifact arising from the real world. So we first try to generate training data from our simulator and then apply to the measurement data collected from the phones. We start with the simple ways of generating the training data using single pass. But interestingly, even such a simple way of generating simulation data already shows feasible for motion tracking. We can get a 1.9 centimeter error, but this error is higher than FMCW processing. Next, we try to add white noise. We add a different amount of white noise, and that allows us to reduce the testing error to 1.1 centimeter. We further add multipass. We vary the number of multipass and the relative distance between different multipass. It significantly reduced the testing error collected from the real measurement. Furthermore, we see that even though we already perform interference cancellation, but there are some still residual self-interference remains. So in our training data generation, we also add a random amount of residual self-interference, and we see further reduction in the testing error. Finally, we found that speaker and microphone has a diverse frequency response, especially in inaudible range, because the existing speaker and microphone are not well optimized for these frequencies. So we emulate the different frequency response and add that to the simulator. And this further reduced the testing error to 0.42 centimeter. And this is already much better than the FMCW based approach. So we basically get the training data from our synthetic simulation, and then collect a measurement from 11 forms of different models and at different environments and with different targets, and also introduce a different amount of interference. And this is one of the results. As we can see, when SNR is high, like 10 dB all the algorithms perform very well. But as SNR reduces, we see a higher benefit of machine learning-based approach because it is able to source through all the data and learn the pattern. So far, I have talked about a few tracking approach. Next, I will briefly introduce some of the application we developed. The first application we developed is indoor follow me June. There are lots of indoor ceremonies that are memorable that we hope to videotape, like a wedding, like your baby's first move, and also some outstanding performance in sports. It is very expensive and time-consuming to have a photographer to videotape every moment. So one way is we could just leverage the drone to videotape. In order for the drone to videotape and produce high-quality video, the drone need to maintain a constant following distance. Moreover, it should maintain a favorable following orientation so that the target is at the center of the picture. So this involves two issues. First of all, we need to track the target. GPS is widely used tracking approach, but it only works for outdoor. Computer vision can also be used, but they are either inaccurate or too expensive. Moreover, in addition to tracking the target, we also need to make sure the drone is moved properly to the right location. So we need to have a good control. The simplest control is the PID controller because it lacks predictive power, so it has a drifting problem. We build on our existing acoustic-based tracking to enable indoor drone, follow me drone. Acoustic-based tracking can achieve high accuracy, wide availability, and low processing cost. But in order to apply it to follow me drones, we need to address additional issues because the target may move around many furnitures, so there could be severe multipass. Moreover, drone itself can emit a strong propeller noise. To address these issues, we developed a new version of music for distance estimation. In order to apply it for distance estimation, we need to compensate the speaker and microphone distortion. Moreover, in order to combat propeller noise, we remove false peak in the spectrum and also apply common filter. Furthermore, in order to enable real-time tracking, we developed a subsampling-based approach. For the control, we use model predictive control because it can predict the future states and take action in advance so that we can minimize the drone's fluctuation. In order to predict the future state, we leverage our tracking to estimate users' velocity based on the Doppler shift. And then we predict the user's future velocity based on its history and integrate the MPC with our tracking. And here is our resulting system. We implemented on the mobile phone. The app will first take the raw audio sample from the microphone and produce the target position and feed that to the MPC-based controller to output the command to send to the drone. Here is a short demo of our system. Basically, we mount a mini speaker on the drone to emit inaudible sound for tracking, and the phone running our app receive the audio sound to real time process it and locate the zone. And interestingly, a nice thing about this is that the mobile phone, because acoustic signal can penetrate certain objects, so in this case, you can see even when the mobile phone is in the bag, the drone can correctly follow the user. Finally, let me briefly introduce our acoustic imaging. Acoustic imaging has been widely used in medical health. It can penetrate certain materials. And what we want to enable is, can we have acoustic imaging based on our smartphone? So by purely running an app on the smartphone, we want to enable acoustic imaging. So for example, you can just swipe your phone across a user to detect a weapon. The challenging for enabling acoustic imaging on the smartphone is that, first of all, there's a strong self-interference because speaker and microphone are almost co-located. Moreover, smartphone comes with a limited number of speaker and microphone, which is very different from the ultrasonic in the hospital, where you have multiple speakers and many microphones. Moreover, we have very limited bandwidth to work with. Ultrasonic has megahertz range, whereas here we only have a few kilohertz in audible range that are supported by your mobile device. To overcome the limited speaker and microphone, we use the synthetic aperture radar. So the idea is by using the movement, we want to synthetically emulate multiple antennas. And through SAR, basically we can map a point in the physical location to a point in the frequency. And this mapping is one-to-one and linear. Therefore, by analyzing the shape in the frequency domain, we can recover the shape in the physical domain. But there are multiple challenges to apply SAR in this case. First of all, we need to overcome self-interference and background interference. Moreover, even though we want the user to move the phone around the desired trajectory, but there is inevitable deviation from the desired trajectory due to hand jitter. There are some existing algorithms that can estimate and compensate for this deviation, but these algorithms assume narrowband signals, point reflectors, no quantization error. But unfortunately, none of these assumptions apply in this acoustic inaudible signal. Moreover, the commodity devices, their speaker and microphone has significant distortion in the frequency. To address this, we developed the following systems. First, we have an interference cancellation module to remove the self-interference and background interference as much as possible. Then we developed a new way of estimating and compensating hand jitter, and then feed the post-processed signal to SAR. Finally, to overcome the uneven frequency response of the speaker and microphone, we developed a compressive sensing-based approach to estimate the frequency response impact and recover the original image. And this is a short demo of how our system works. The user holding the phone and move around a desired trajectory. and then collect the audio sample and produce the image in real time. Here is another sample. In this case, the object is out of sight, but interestingly, acoustic signal can penetrate through this plastic bag, so we can still support imaging. So to summarize, I show that it is feasible to use acoustic signal for motion tracking, and it works on a variety of devices, on smart speaker, smartphones, smartwatch. Of course, the application dictate the design of tracking technologies. We have done some outreach. We have done some demos at CES and South by Southwest. Also have some news coverage. Besides the above acoustic-based tracking, our group has also recently done some work on tracking a human voice. This is also an interesting and different problem. Unlike existing tracking, we rely on non-signal. Human voice is out of our control, and it's also hard to predict. So we developed a new approach to estimate the angle of arrival of human voice, both from the direct path and also from the reflected path. Meanwhile, we also come up with a cheap way of estimating the room profile. So combine these together, we can trace back the human voice position. We also have done some work of using RFID for temperature sensing and rotation sensing. And if you are interested, I'd be happy to talk about more. Thank you everyone for your attention. I'd be happy to take some questions.
Thank you, Professor Chiu, for that very fascinating talk. A very impressive set of signal processing work coupled with some amazing applications. We have a number of questions. Let me ask them in some order. I'm actually trying to figure out how I can see the questions, all the questions. Okay. One question was asked by Ajay from Ericsson. It's on millimeter level positioning seems to be quite critical for robot positioning within industrial environments. He was wondering whether this techniques could be applied to an industrial environment. I'm guessing the concern there will be acoustic noise in the environment itself. Like what happens if you're doing this in a really noisy environment, say an industrial environment, trying to position, say, manufacturing robots, etc.
Yeah, that's a great question. So first of all, depending on the noise, in fact, because we are using the inaudible frequency band 17 kilohertz and above, so if the noise is below that, we are robust to it. In fact, in almost all our acoustic work, we have been testing against the typical background noise, and sometimes we also stress test by playing rock music in the background, and they don't cause any performance issues because they are on different frequencies. And but if you do have the noise at the frequencies, like in the case of June, if the noise is known at a particular frequency, we have some technique to overcome it.
Okay. Okay. Another question that was asked was from Vishal from ISC. Have you tried tracking the sign language that deaf people use? Interpreting the sign language could be a really good application.
That's a great application. In fact, yeah, that's one of the applications someone also suggests to us. We haven't developed that application end to end, but we have done some feasibility studies. So basically, we let the user try to distinguish when the user is drawing different digits. We found that just by simple pattern recognition, we can tell which digit the user is drawing. So it shows the potential of applying this acoustic-based tracking to sign languages.
Okay, and just to, sorry, I didn't mention this. I was going to take one last question from the virtual audience, and then I will switch to the physical audience, right? So the physical audience will get at least 10 minutes to ask questions. So don't get worried, those folks in the room. I forgot to mention this, sorry. The last question I'm going to take from the virtual audience is there an error bound guaranteed by the system? This is from Jay from Ericsson again. This may be critical for safety-dependent applications, such as drones, to know what the error bound would be. Is there any guarantee on the error bounds?
There is the common raw bound based on the number of microphones and the SNR. There's some theoretical bound. But those theoretical bound is not necessarily tight, but at least we can use it as a guidance.
Okay, and now we can switch over to the physical audience. Bishak, do you want to take over and pan the camera to the mics, for example?
Okay, very nice talk. I have a question. So can your technique track multiple identical objects simultaneously?
Can you introduce yourself first before asking a question?
Pratik Mukhopadhyay from LSU.
Thank you for your great question. Yeah, indeed. If two objects are well separated, then we can track them simultaneously.
Yeah, hang on a moment. Hang on a moment. Bishak, you need to mute the mic after the question is asked. Otherwise, there's horrendous echo from the room. Thank you.
When multiple objects are well separated, then we can track them simultaneously without problem. But when these two objects are close enough, then they will have merge peak. In this case, there's some challenge. And the resolution depends on the bandwidth. So if we have more bandwidth, then this is less a problem. Moreover, there are some machine learning technique we can use to further improve the resolutions, because as we mentioned, object movement are continuous. So if two objects are far apart initially, you can track, and then they are crossed and then separate. Then machine learning based like RNN approach can allow us to track even when they are close enough, because we can leverage the temporal locality of their individual objects' motion.
Okay, can we take the next question from the room? Need to unmute.
Hello.
Yes, go ahead.
Hello, Professor Q. I'm Manupriya Gupta from IIT Delhi. So I had this question related to this tracking and how you're tackling the distribution of mass in it. So you showed us a demo of moving two objects simultaneously and you're tracking them independently with no interference. So I had a question. Let's suppose a hypothetical situation when these two objects are connected by some massless string or something, and their motion is also identical. So in that case, will your algorithm be sensitive to the distributed mass? Will it be considered as one object or two objects separately? So in a nutshell, it's about how sensitive it is to mass and distributed mass.
How sensitive to what? Sorry, I missed the last part.
To mass and distributed mass. The algorithm.
To the mass of the object and the distributed mass of the object.
Okay. So first of all, there is a difference between tracking device or tracking device free. If we are, so one of the demo I show you that you have multiple smartwatch, and so each of these devices has separate receiver. Then, in fact, in those cases, it's we can support tracking of many of these objects, because each of these objects receive the sound signal directly from the transmitter, and each one can just track independently. But device-free is the case that is more challenging because if you have two hands, then their reflection are mixed, and the receiver, there's a single receiver that received some of their individual reflections. So in that case, it depends on the resolution. If these two hands are far apart, then it will show as separate peaks. Then we can individually track them. But if they are close within the resolution, then it will show up as a merged peak. So the resolution is solely determined by the bandwidth, and whether we can track these multiple objects simultaneously in this case depends on their separation. It's not related to their weight and other facts. Did that answer your question?
Okay, can we have the next question from the room? The camera is
Oh, can you hear me now? All right.
Yes.
Hi, Lili. This is Varun Kumar from Carnegie Mellon.
The camera is off.
Yeah, I noticed that. I don't know what's going on, but
Okay.
they're trying to fix it. But anyway, I'll go ahead and ask my questions in the interest of time. So I wanted to ask about acoustic localization in general, where that applies for gesture tracking and sensing. I know you yourself have worked on RFIDs, on...
Oh, we lost Varun. Your mic is muted.
Can you hear me again?
Yes, you're back.
Okay. Quick, short question. When is acoustic the best solution versus Wi-Fi, RFID, and so on for gesture tracking?
Oh, that's a very interesting one. Thank you very much for the questions, Warren. I'm great to be here. So I think one of the major benefits of acoustic is it's the wider availability. It doesn't require some special hardware, and also it can penetrate certain objects. Wi-Fi is very appealing for long distance tracking. And the millimeter wave is also very attractive for short range tracking. Acoustic has a role to play because mainly because the less requirement on the hardware, and also let me see. Compared to Wi-Fi, it has a higher accuracy. Compared to the millimeter wave, the range is better, especially for the device-based. Another interesting advantage of acoustic tracking is we can also track natural sound that already in the environment. So the combination make it a unique, it's likely to have a unique role to play in the future sensing and motion tracking.
Hi, am I audible?
Yes.
Yeah, hi Lili, Rajiv Shori from IIT Delhi. I was just curious to know, could you throw some highlight on accuracy improvement through deep neural networks? What kind of networks are these, and specifically, do you really see key benefits with the ML and deep learning as far as the accuracy and the performance improvement is concerned?
Yeah, so the we do see benefit of ML-based approach. And in fact, we also learned some lessons from the ML-based approach. So for example, in traditional FMCW processing, we only use the signal part and we threw away noise. But when we just feed a raw signal to the machine learning technique, we found that even the noise part, when the transmitter is idle, it also has some useful information, and machine learning technique is able to leverage that. And this may also help us redesign the future signal processing approach. And also signal process, and also machine learning, it learns different weights for FMCW received signal. So it shows that even though the FMCW, the one we are currently using, is sound, but there's room for improvement, and there's something we can learn and feedback to the signal processing as well.
Okay, next question from the room.
Hi, I'm Soma. I'm from Geo Platforms, from a telecom company, basically. My question is that what is the longest distance that you have achieved between the object and the detector, the sensor? What is the maximum distance that you can detect from?
Sure. Yeah, for the device-based, we used like a pretty powerful speaker. We are able to achieve 20 meter above tracking. And for device free, it's more challenging, but the best we can achieve is above, it's between 3 to 4 meter device free using the Bella setup I showed in the demo.
Okay, one last question from the room, or second last question. No, I can't see the videos because, okay, I have a question, Lili. These techniques are all great, but do they have any impact in the inaudible frequency on animals? Like, is your lab an animal-free zone because they go crazy with hearing the high frequency signals?
Oh yeah, concern about the animal.
Correct.
So
for general deployment.
There's some numbers. Let me try to see if I can. So we compare with the FCC requirement of the energy generation, and compared to the FCC requirement, we are at least one order magnitude lower. So it's not a big concern. And also these acoustic signal are mainly refracted by the skin. They are not going to be absorbed. Furthermore, we also done some empirical study. We just bring our phone, emit FMCW signal and walk around the pet store, and we don't see any significant disturbance to them.
Yeah, that was my concern, whether dogs would react because they tend to not like very high frequency sounds that we can't hear. Okay, for some reason we lost our video because I wanted to show you the room. Even though it says there's only 32 people online, the room is actually packed. There's about 70 people in the room, and most of them are students who are supported by the generous grant from SIGMobile, which came through you and Jennifer. So we'd like to thank you again for providing the awesome support from SIGMobile that allows these students to quickly show up. But unfortunately, we don't see that video feed, because you could see all the attendees yourself, and the generous support, which we hope will come every year, right?
Excuse me, sir. One last question, please.
Okay, go on, Ms. Chop.
Yes. Hello, Professor Lee. I'm Naveen from IIT Hyderabad. So I have a question. When you show the existing approaches as a computer vision as an approach. So we have in a computer vision based solution, we have state-of-the-art object detection plus tracking approaches, which are used in autonomous vehicles, drone technology as well. And just now you answered about the distance as well. You are able to accurately using the acoustic signal tracking. You are able to do up to 4 meters around. But how do you compare with the computer vision based tracking with respect to the distance and accuracy? And second question is regarding multi-object tracking that you showed with
Hi, we don't have time for 2 questions. We're already out of time. So
Okay, so that's the first question. Yeah, that's the only question.
Can we have a quick answer?
Yeah, computer vision technique, first of all, it raises privacy issues and also has more energy consumption. And also in terms of range, we played with Intel RealSense. It cannot achieve 4 meter range. Maybe the newer version is better. The version we played with only achieve 1 meter range. And of course, it's arm race, but I think acoustic, especially for privacy preserving scenarios, can be attractive. Not everyone would like the camera on all the time. Yeah, so like for health monitoring at home, you might want to discreetly using it for certain event detection. That might be very attractive.
Okay, well, shall we all once again thank Professor Chiu for an amazing keynote. As a show of our generous appreciation, we'll be sending you an Amazon gift voucher very soon, because we are not sure. Yeah. So this is what the appreciation voucher will look like, and you'll be getting it very soon. In terms of announcements, there will be a break now for half an hour, and then please come back for the first session of the technical program along with demos, etc. So without any further ado, I'd like to thank Professor Chiu again and end the first keynote session.
Thank you so much, everyone. Thank you for the kind invitation.
Thank you. Thank you, Lili. That was a very impressive talk, very engaging. Thank you.
Thank you.